I shall talk about dilution cooling. Let's start with a simple example of a cooling effect. Imagine there is some water and the water evaporates. As the water evaporates, it cools down. Now, we can use this as a way to cool things down by, for example, pumping away the vapor. Right? As the water vaporizes, it happens because molecules with higher kinetic energy in the water happens to escape from the water surface, so that the average energy of the remaining water molecules decreases. So that's why the water cools down. And we know, for example, that if there is a wind blowing at the water will cool down faster. And that's because the wind removes the water molecules from around the water surface, and that prevents those molecules, because of random motion, for some of them to come back to the water surface, into the water. So by removing the water molecules in the vapor above the water, we can help the water to cool down faster by removing those molecules that return to the water. So in that sense, that's the idea behind pumping away the vapor. So we can imagine attaching a pump to it, and when we start pumping away the vapor, alright, we remove the water molecules that return to the surface, and therefore the water molecules keep going out, and then the water cools down. So this is the idea of cooling by pumping away the vapor. Now, but in such a cooling method, there is a limit to how far the temperature can go down. The reason is because as the water cools down, the rate that water vapor comes out of the surface, the rate of the vaporization decreases. So as the temperature falls, it will cool more and more slowly until it reaches a certain limit, and then it will stop, or effectively stop cooling below that temperature. Now let's take this idea over to cooling at very low temperatures. If you think about, say, liquid helium, let's say this is liquid helium, right? Now in liquid helium, the temperature is a few kelvins. So usually we think of, say, for liquid helium-4, the boiling temperature is at about 4 Kelvin. So we usually associate liquid helium with this temperature of 4 Kelvin. Now we can cool this down further by using this evaporation, and we can help this to happen by pumping away the vapor, just like we can do for water. So if we pump away the vapor, that would force the liquid helium to cool down further, and usually this method can bring the temperature down to about 1 Kelvin, but it cannot go down below that. The reason is because as the temperature falls, the amount of vapor that escapes the surface decreases, and it decreases exponentially. Now by exponentially, we're thinking in terms of perhaps something like the Boltzmann factor, So exponentially in this sense, as temperature decreases, right, this exponent, the argument goes to minus infinity, and this Boltzmann factor becomes very small. So the idea is we can understand this by thinking that this Boltzmann factor could be an estimate of the amount of vapor that could be an estimate of the probability that the helium atoms would go from the liquid to the vacuum above. It's like the vapor, the helium molecule has to have a certain energy before it can escape into the space above. Okay, so that could be the energy there, which could be the energy needed to break the forces of attraction. So there is this very rapid decrease in the vapor pressure as a result. So that limits the lowest temperature that it can go down to. Now in this method of dilution cooling, we are interested in bringing the temperature all the way down to the millikelvins. So that is a lot lower than 1 Kelvin. And in order to do this, therefore, we need a completely different method. We can't just do it by evaporating the helium, the liquid helium anymore. So the way to do it, there are a few. And for this topic, we are going to look at what is called the dilution cooling method. And this is what is involved. Imagine, again, a bucket with some liquid inside. Now, there are two layers of liquid here. The top layer is liquid helium-3, and the bottom layer is liquid helium-4. Okay, with a little bit of liquid helium-3 mixed inside. So, using this method, the liquid helium-3 from the top layer would diffuse into the liquid helium-4 below. And when this diffusion takes place, it will cool down. And using this method, it is possible to cool down to the millikelvins. Now this looks like a rather strange setup, and the purpose of this topic is then to understand how this works. So for a start, let's look at helium-3 and helium-4. Now helium-3, the helium-3 atom consists of 2 protons and 1 neutron. The helium-4 atom has 2 protons and 2 neutrons. So that's why the 3 and 4 are the mass numbers. Now the mass itself, the actual mass of each atom, we can find by taking, say for the helium-3 atom, 3 times the atomic mass unit. And for helium-4, that would be 4 times the atomic mass units. So these are the basic data for helium-3 and 4. Now the other thing is that helium-3 is a fermion and helium-4 is a boson. Right? The reason is that each of the proton and neutron has a spin half, just like an electron. So for helium-3, the total spin of the three of the protons and neutrons is half, but for helium-4, the resultant spin is 0. So that's why helium-3 is a fermion, and if it's a fermion with a spin half, that means that, like the electron, helium-3 would obey the exclusion principle, whereas helium-4, being a boson, would not obey the exclusion principle, and you can have any number of helium-4 atoms occupying the same state, but you can't for helium-3. Okay, so these are the basic data for the two. Now let's have a look at next a mixture of helium-3 and 4 to understand how it is possible to get the two layers of liquid that I showed. Okay. Now, just so we have a good idea where we are heading, let me sketch out a rough plan of what I'm going to talk about. So the idea is to understand eventually how this setup with the two layers of liquid of helium-3 and 4, how it can produce a cooling effect and cool things down to such a low temperature. Now, in order to do that, first we need to understand how it separates into the two layers. So we'll look at a phase diagram of the mixture to see how a mixture of liquid helium-3 and 4 behaves at different temperatures and concentrations. And then after that, we will make use of the fact that helium-3 is a fermion. And the fact that it's a fermion means that it obeys the same statistics as an electron, and that also means that what we have learned earlier about the heat capacity of the electron can be applied to helium-3. And since we can use what we know about electron heat capacity, that means that we can take over the same formula and calculate the energies and heat changes related to helium-3. So, and it is because of this that we can then work out what happens when helium-3 atoms move from one layer to the next layer by looking at the heat capacities of the helium-3 atoms in each layer, and then we can work out that there is a cooling effect. So let's start with the phase diagram. Now, in this phase diagram, we think of it as a graph with temperature on the vertical axis and the concentration on the horizontal axis. Now the concentration here refers to the fraction of helium-3 atoms in a mixture. So we want to think of a mixture of helium-3 and helium-4 in a liquid. So this means that we are talking about 1 Kelvin or a few Kelvin, very low temperature, so that the helium is already a liquid. So we are thinking about such a mixture, and the x here would be the fraction of the number of helium-3 atoms. Let me write this down. With a number of helium-3 atoms divided by the total number of atoms. So that's the x. So the range goes from 0 to 1. Okay. Now the temperature of interest is just a few Kelvin, so let's say that's 1 and that's 2. Okay. Right. And the phase diagram looks like this. The phase diagram consists of 3 parts. These 3 parts. Now, for example, when if you think about, say, a certain point in the graph, a point in the graph refers to a particular concentration of helium-3 and a particular temperature. So that's what a point in the graph means. So a point in this area would be a mixture of helium-3 and helium-4, and that's just it. It would be just a mixture. Okay. Now, a point in that area, however, it would also be a mixture, but with a difference. If you have this particular concentration and this temperature, this would be a superfluid. Now, superfluid is a fluid that can flow without any resistance. So that means that, in contrast, if I'm at that point in that area, this is a normal fluid. So when this liquid flows around, there would be resistance, viscosity. Okay. Now, and if you imagine, say, starting from a certain concentration, but at a higher temperature here, as the temperature lowers, at some point it crosses a temperature where it changes from a normal to a superfluid. Okay, and that's what this line represents. If you start from any point and you lower the temperature, then when you cross that line, the normal fluid becomes a superfluid. And there is a name for this line. It's called the lambda curve. Right? So that's that. Now, but for the purpose of this topic, for the cooling method that we are talking about, it is this region which is more interesting. Now this region here is actually a forbidden region. It is not allowed. What exactly does that mean? Let's imagine that we start from, say, that point. Start from a point there, with meaning that we have a mixture with a certain concentration of helium-3 at a certain temperature. So we start from that. So, and then taking this mixture, let's imagine that we start cooling it down. So as it cools down, the point moves downwards, and that just means that the temperature falls, but the concentration is still the same. And when it reaches this curve here, this shaded area, let's say we bring it all the way down into a temperature inside the shaded area. Now when we say it is not allowed, it means that it is not possible to have, at this temperature, to have the same concentration, to have this particular concentration. And what actually happens at this temperature is that the mixture will separate into two layers. One will get a higher concentration of the X, and then another would end up with a lower concentration. So if you imagine you have this container of the mixture, then when you lower the temperature to around there, you will see the liquid separating into two layers. Okay. And one layer will have much higher concentration in helium-3. The other layer would have a much lower concentration of helium-3. So we call one layer the concentrated layer, and we call the other layer the dilute layer. Now, the concentrated layer means that it is more concentrated in the liquid helium-3. So we have so far I've been thinking in the terms that it is the helium-3 that is dissolved in the helium-4. Alright, so when I talk about concentrated, I'm talking about the helium-3 being concentrated. Now notice that I've drawn the concentrated phase, as we would call it, sitting on top of the dilute phase. And the reason is this. It is because the helium-3 atom is lighter than the helium-4 atom. So therefore a mixture that is more concentrated in helium-3 would be less dense than a liquid that is dilute in helium-3, because the dilute solution will have more helium-4, which are heavier atoms. So this is what happens, and this is what this forbidden region means. It is also called a phase separation region. And when so that when the temperature falls into this region, the mixture would separate into the two phases and you end up with two layers. So that's how we get two layers in the liquid, because of this property. Okay. Now for the purpose of this method, this cooling method, we are interested in the temperature, a temperature which is quite small, which is quite close to zero on that scale, and that's a temperature that is of the order of millikelvins. Okay. Now at such a low temperature, we would be working quite close to the x-axis here, quite close to the bottom of the curve. Now when you are at such a low temperature, the x in this phase, right, that would be the concentrated phase, would be very close to 1, as you can see, meaning 100% helium-3. Okay, so this concentrated layer at such a low temperature is therefore nearly pure helium-3, nearly 100%. And we can often assume that if we are in data calculations. So that would be pure helium-3. Now, at this point, however, when you're at a very low temperature, this curve comes down to a value of x that is 0.066, alright, or 6.6%. So it comes down to this point, and that would be the usual concentration of this dilute phase that we would look at. So this would be 6.6%. That would be pure helium-3 when we are at the millikelvin temperatures. So this is our working system. This is the situation that we would look at, all right, the condition that we would use to produce this cooling effect. Okay, so what I've done is I've described how we can produce this system. The next thing that we need to look at is we need to start thinking about why this system can cool things down. So to understand the cooling part, there are two things we want to look at. One thing is the question about why it cools down. Now, the other thing we want to look at is about why this method can do better than just evaporating liquid helium-4. After all, this method is a lot more complicated than just evaporating liquid helium-4. So we should have a good idea about why this is better before actually building the equipment to do it. So let's think about liquid helium-4. So if you have liquid helium-4 and there's vapor above it, and we pump away the vapor, then liquid helium-4 cools down. Right? Now if we have this mixture, alright, we have this concentrated phase, which I will call, which is the 100% helium-3, and we have a dilute phase down here, which is the 6.6% typically of helium-3. So whereas the liquid helium-4 cools down when vapor is removed from around the surface, or when helium-4 atoms moves up into the space above it. In this case, in the helium-3 mixture, it cools down when helium-3 atoms diffuses into the layer below it. So for now, I'm just going to assume that it would cool down. Right? I'll look into the question of why it cools down afterwards. But for now, assuming that cooling happens when helium-3 diffuses into the space below it, let's think about why this method can do better, can bring temperature down a lot further than just evaporating helium-4. Now, coming back to the helium-4, I've been talking about pumping away the vapor. Now, let's think about what happens if we don't pump away the vapor. If we don't pump away the vapor, let's say if I put a lid over this container, the vapor stays around here, okay? And if the vapor stays around here, it will stop evaporating after some time, because the vapor would diffuse back into the liquid. So I need to pump it away to prevent that from happening. Okay. The only trouble is that as temperature falls, the vapor pressure, or the amount of vapor that can be produced, would drop exponentially. So that at very low temperature, even if you pump it, even if you want to pump the vapor away, there is hardly any vapor for you to pump, simply because it hardly vaporizes. Now in this case, for the liquid helium-3, the 6.6% concentration below in this dilute phase, you can actually think of it as a saturation concentration. So this number here would correspond to the saturated vapor pressure in the case of helium-4 vapor. So the 6.6% is like a vapor pressure, so that as the helium-3 atoms diffuses into the layer below, when the concentration of this layer reaches 6.6%, it will stop diffusing. The cooling will stop. Right? If we imagine that initially the concentration below is 0%, then helium-3 will start diffusing downwards. So when the concentration of helium-3 reaches 6.6%, diffusion stops, in the same way that if you cover up this container, the vaporization stops when the vapor is saturated. So the 6.6% here is like a vapor pressure, and in order for cooling to continue, we need a way to remove the liquid helium-3 from the lower layer. Okay, then it's not saturated anymore and it can continue to diffuse. Now the difference here is that as the temperature falls, the saturated level remains at 6.6%, as we have seen from the phase diagram. Unlike the case of helium-4 vapor, where the saturated vapor pressure drops a lot with temperature. In this case, the 6.6% stays the same, no matter how low the temperature goes. So it is as if the 6.6% is like the saturated vapor pressure, it is as if the vapor pressure does not change with temperature. So no matter how low the temperature is, it can still continue to diffuse downwards. Alright, this 6.6% saturated value does not change. And it is because of this that the diffusion can continue to happen even if the temperature goes to a very low value, well below what you can get with liquid helium-4. And that is why this method has the advantage over this method. Alright, for evaporating helium-4, evaporation stops because the rate of vaporization drops very rapidly. But in dilution cooling, the diffusion continues. Alright, because the saturated concentration remains fixed. So this is a main reason why it is possible to use this method, this dilution cooling method, to reach temperature that's much lower than evaporating helium-4. And the next thing that we now need to look at is why the cooling takes place at all. And we will do that in the next session.